Previously, differentiation was discussed as a method by which we can work out the gradient of any point on a curve, so long as we know the equation. Well, what if instead we wish to know the area under the curve, or the area between the curve and the axis? This is where the alternate topic, integration, comes in. Now, for integration, we're actually going to do the exact opposite steps of differentiation. If we were to start again with this model of y equals ax to the power of b, so some amount of x to a given power, the integral of y, so this like stretched s for the integration sign, the y, and then this dx here, which you may recognise from doing dy over dx in differentiation, is saying just with respect to x. It's x that we're changing. This would come out as the coefficient divided by 1 more than the power, with then that power having had 1 more added onto it. Just for some numerical examples, so it's clear on what we mean by that. If we were to start with a singular 4, now we can imagine that that has like an x to the power of 0 next to it. Now if we were to add 1 to that power, that would now become to the power of 1. And then we'd have 4 divided by that 1, which is just 4. So if we were to integrate that again, if we raise the power by another, that would bring it up to a power of 2. Then 4 divided by this 2 would now get us 2x squared. Actually, if we just keep the simplified forms underneath. To integrate that again, if we raise this power, that becomes a cube, and then 2 divided by this 3, and so forth. This would keep going as many times as you needed to, although it would be very rare that you would need to do it more than once, at least in pure. In mechanics, you may end up having to do it twice, but again, that should be it. Whenever you're doing integration of this style, though, we'll call this an indefinite integral because we're just trying to come up with a generic equation. When you do this, you have to add at the end a plus c whenever you're done. And this is basically to signify the fact that we are unaware if any other term would have existed in, say, the original equation. Let's say, rather than starting with y equals, we're starting with dy over dx equals. We're starting with the gradient you have previously differentiated. Let's just say up here that you had started with y equals 2x plus 6. To do the dy over dx, that would just become 2, because power times coefficient, 2 times 1 is 2. Take 1 away from the power, that now becomes a power of 0. X to the 0 just has a value of 1, so 2 times 1 is 2. Then here, x to the 0, so 6 times 0 is 0, disappears. If now, however, we had started with this 2, and you want to integrate back up, we could say that this 2x, because it's like x to the power of 0, add 1 to the power, becomes a 1, and 2 divided by 1 is 2. You get your 2x. But we have nothing that tells us that this used to be a 6. We cannot know, without any other context, what that number used to be. Now, if, say, you were then told in the question, actually, this line, this y equals mx plus c, goes through a specific point, you could then plug in your x and y values to get this missing c, like you would for a regular straight line, or it works the same with a curve in this case. So long as you have x and y coordinates, you can plug in and solve. But if they don't give you that, the best we can say is that it would integrate back again to just be 2x plus c, the plus c here. Now, that is only, as I say, if we don't have coordinates or we don't have what we're going to call bounds. If this is an indefinite integral, this is an definite integral, because now we're going to have some numbers on the top and the bottom of it. And that is to say, not only are we looking just for a general expression for what the area would be under the curve, we're now looking specifically for an area between 2 points. Let's say that we were integrating x squared minus 4, which will look something like this on an axis. First of all, integrating, so the x squared, add 1 to the power, it becomes a cube, and then this basically coefficient of 1 gets divided by the 3, so it's a third x cubed. and then the minus 4 becomes a minus 4x. As you raise 1 to the power, generates an x, and 4 divided by 1 doesn't make a difference. If now, though, let's say we specifically wanted the area that was between 2 and minus 2. Okay, so this area between this x-coordinate and this x-coordinate, that would be this part of the graph here, between the curve and the axis. In that event, your bounds would now be those x values, so the higher x value on the top and the lower x value on the bottom. What you then do is you do this equation once where x is that upper bound. So in this case, it would be b for the generic, but in our example, you now do it as 2. So a third of 2 cubed minus a 4 times 2. And then this is minus doing it again, but now with the lower bound. So now instead of x, you have your a value, in this case the minus 2. So a third of minus 2 cubed minus 4 lots of minus 2. And you put that in your calculator, and that will give you the area specifically between those 2 points. Now if instead, rather than just doing your 2 and your minus 2, the question had rather asked about this area here between 0 and 3. We wouldn't just do, say, your integral there with an upper bound of 3 and a lower bound of 0, for the reason that this curve has crossed the x-axis. And what this means is mathematically, any area that's underneath the x-axis is going to come out as a negative because it's in the negative region. Of course, because you can't have a truly negative area, what we would usually do, like in the previous example here, is we would ignore the minus in front and just take the regular number. But if we were to do this all at once in a single equation, what the equation would do is it would work out a positive value for this area here, then work out a negative value for this area here, and when it combines them together, it would take the areas away from each other, rather than adding them together to get a combined total area. So instead of doing your 3 to 0, what we'll do is we'll do it once with 3 to 2, then you'll do it again with 2 to 0, and then once you have this value, ignore the minus, and then add them together. If those principles are okay, let's just go through some examples of how you're going to integrate and then one of how you apply that to a graph. So to start off with, if we just want to integrate x squared minus 7x plus 9, well, like we had down here with this x squared, if we add 1 to the power, you end up with an x cubed, and then the coefficient of 1 in front, there's one lot of x squared, that gets divided by this new power of 3, so a third x cubed. Then here, we have minus, raise 1 to the power, that now becomes x squared, and 7 gets divided by that too. And here, that plus 9 becomes a 9x, as the x to the 0 rises to become x to the 1, and divide by 1 makes no difference. At the end, just don't forget, plus c. Maybe though, the equation that it gives you at the beginning is a little more complicated. We'll still be able to integrate this, but we'll want to simplify first. In this example, clearly it's a fraction, but it may also be that the thing is in brackets, and you want to expand those brackets first before integrating each term. In this case, the 3, I was just going to say 3, here, because we're going to be dividing by x to the half, just as how if you have like x squared times x cubed, you would add the powers together to get x to the 5, and if you divided, you have like x to the 7 divided by x to the 3, was x cubed, you'd minus them, so 7 minus 3 is 4, so x to the 7 divided by x cubed will be x to the power 4. Here, because we're dividing, x squared divided by x to the half, you're going to take them away, 2 minus a half gives you now 5x to the power of 3 over 2. Meanwhile here, we just have 2 over x to the half. This term in the middle now is easier to integrate, but the final one, it's still a fraction. So what we're going to have to do next is rewrite that as just x to a power, rather than being in a denominator. Now, if we're not entirely sure from topics on indices, if you have an x value in the denominator, you can bring that up as just a regular x, but what you have to do is say it's now minus that power. So now that's going to be a minus half here. The 2 just stays a regular 2 in front. Now that all of this is in individual terms that we can now more clearly visualize as like an ax to the power of b, now we can integrate. So the integral with respect to x is going to be, so 3 becomes 3x. Here, adding 1 to this power gives us 5 over 2. Now, 5 divided by 5 over 2, that's just going to leave you with 2. So 2x to the 5 over 2. And here, add 1 to the power is now a half, a positive half. 2 divided by a half is going to give us 4. So it's now 4x to the positive half plus c. And then finally here, just with some find the area R. And we've got this just sketch of an axis here, where this curve has the equation y equals 2x plus 8 over x squared minus 5. And the area R is bound between the curve and not the axis this time, but rather this line between points P and Q, where P has x coordinate 1 and Q has x coordinate 4. Well, what we can do with a question like this is to say, if we were to just join up these points here, if you were to just work out the area between PQ and the axis, that in this case would get you a solid trapezium. Then, if you were to work out what the area underneath the curve would be, so this bit here, and do the trapezium minus this area, that will leave you with R. In these kind of questions here, we've got some other line than the axis that you're now bound between. Just think, what would make the bigger shape if you were to join up these like points like P and Q with the axis, and what would make the smaller shape? Is it the area under the curve, or is it the other thing? And just do big minus small. So, in order to start off with, if we're going to work out the area of this trapezium, we need to work out the y-coordinates of P and Q, as well as their x. Well, because we know that P and Q lie on the curve, we can just plug in their x-coordinates to see what the y-coordinates are. So we're saying y equals 2 lots of 1 plus 8 over 1 squared minus 5. That's going to be like 2 plus 8 minus 5. That's just going to leave us with a value here of 5 for P. And then next, if we do the same with the 4, so y equals 2 lots of 4 plus 8 over 4 squared minus 5. Well, that's 8 plus 4 squared is 16, so 8 over 16 is like a half, and then minus 5. That's going to give us 3.5. To work out the area of a trapezium, you're then going to do half the sum of the parallel sides times the distance between them. So half. Then for the sum of the parallel sides, sum means add. The parallel sides, in this case of this four-sided shape, are between P and the axis and Q and the axis. So the length of this line here is 5. And the length of this line here is 3.5. And then times the distance between them. In this case, the distance between them is 3. So between 1 and 4. Putting all that into the equation, and solving in the calculator, you get an area of the trapezium of 12.75. Now that we have the trapezium, we can just go about working out the integration. If we just move this stuff out of the way, keep that up there. So that's the area of our trapezium. Now to integrate y with respect to x, the 2x here, raised to the power by 1 gets you x squared, and then you're going to have 2 divided by 2, which of course we know is just going to become 1, but I'll do that in a second. Here, because this is like x squared in the denominator, as we had above, if it's in the denominator, you can say it's like the same thing, just to a negative power. So this is like 8 to the power of x to the minus 2. So raise the power by 1. That's now going to take us up to minus 1. and then 8 divided by minus 1 is what that gives us there. And finally, well, you would have minus 5x. I say finally, even though we should have a plus c, because of course we are about to put this into bounds here in a second. So just to simplify first though, x squared minus 8x to the minus 1 minus 5x. Now of course this is between 1 and 4, so we just put my 4 and 1 here. This is now in brackets of 4 and 1. Just to clarify from before, because I don't think I said, the reason why we don't need a plus c when we have the definite integral is that when you're taking these brackets away from each other like here, you would have a plus c here and a plus c here. And they're not going to change because they don't have an x value. So when you're taking them away, you just end up with a c minus c, which of course just disappears. So it doesn't actually matter what the c value would have been. So yes, it technically does exist, but in terms of just finding the definite integral, the area between these points, it doesn't make a difference, so we can just ignore it, so long as we remember to put it in the indefinite integrals. So anyway, here, we'll do this equation once, where we have, so 4 squared minus 8 times 4 to the power of minus 1, minus 5 to the power of 4, no, sorry, times 4, and then minus from that, doing 1 squared minus 8 times 1 to the minus 1, minus 5, lots of 1. Doing this, you should get an overall area under the curve of 6.75. Finally then, if we just do the whole trapezium minus this area under the curve, you end up with 12.75 minus 6.75, which gives us an area of 6. There aren't any units in this case because no scale has been given here, it's just the x-axis, so it's just 6. If we're good with that, let's then just see what we want to do with an actual exam question. So let's say here we have this graph, which is not to scale, just to stop you from taking measurements with a ruler and whatever. So figure 4 shows the sketch at a part of the curve C with the equation y equals 32 over x squared plus 3x minus 8, where x is greater than 0. Now the point P, which has coordinates 4, 6, lies on C. The line L is the normal to C at the point P. The region R, shown shaded in figure 4, is bound by the line L. The curve C, the line with the equation x equals 2 and the x-axis. Show that the area of R is 46. And below that, just saying, yeah, we need to do this by integration. We can't just try to measure the area on the page using like physical rulers and stuff. So what we're going to want to do first is actually split up this shaded region so that on the left we have the integral of the curve between the x coordinates 2 and then this x coordinate here is going to be 4 because it's the x coordinate of P. So the area between the curve and the axis here. And on the right, this is actually just a right angled triangle. So if we can work out the height, well, we actually already know the height. The height is going to be the y coordinate of P, which is going to be 6. And then what we need is the base. So the distance between this 4 and some unknown x value here. If we can work that out and then just add the two areas together, that gets us the shaded area, which, because it's a show that question, we know should be 46. We'll start off then by dealing with this straight line, working out its equation, because with it we can work out this missing x value. Because we know that the line L is the normal to C at P, the normal, if you remember from the differentiation videos, which if you haven't watched yet, I advise you do, the normal is a straight line with a gradient that is perpendicular to that of the curve at that point. Because we're going to be dealing with the gradient of the curve, any question that has the word normal or tangent, you will be doing so, we need to differentiate. So actually this question shows that we can merge differentiation and integration as already related topics together explicitly in one method. Differentiating this equation then, well first of all, we'll actually just rewrite this first term as 32x to the minus 2, because again, if it's in the denominator, it's like a negative power. So dy over dx is going to give us, so remembering what we're doing this time, we're doing the differentiation, we're doing coefficient times power, so minus 64 x to the minus 3, and then the plus 3x just becomes plus 3. If this is an expression for the gradient, we now want it at this specific point P. We know the x-coordinate is 4, so if we just do minus 64 in brackets 4 to the minus 3 plus 3, in your calculator this first term comes out as minus 1, so minus 1 plus 3, which is going to give us a gradient at P of 2. And this will be the gradient of our tangent. Remember, m is gradient for like y equals mx plus c, and t for tangent, the line that's parallel to that curve at that point. If we also remember from the videos on the normal lines, the gradient of the tangent times the gradient of the normal equals minus 1. So 2 times the gradient of the normal equals minus 1. Gradient of the normal equals minus 1 over 2. In other words, the negative reciprocal, so it's this number here is now in the denominator, and we switch the sign, it became a minus. Because we have this gradient and we have the x and y coordinates of P, we can now create the equation of a straight line. So we can say that y equals minus a half x plus c, and 6 equals minus a half 4 plus c. So minus a half times 4 is minus 2. So 6 equals minus 2 plus c. So c is going to equal 8. So we have y equals minus a half x plus 8. Now, just to work out this x-coordinate here, where it cuts the x-axis. If you cut in the x-axis, your y is 0. So 0 equals minus a half x plus 8. A half x equals 8 if we just add it over, so x equals 16. With this then known to be 16, we can just work out the area of the triangle. So the height is 6, and the base, the difference here is going to be 12. So a half times 6 times 12 is going to give us an area of the triangle of 36. Now we have that done, we can go back to the integration, which is the main focus of today. So we're now going to be integrating this equation here. So the integral of y, integrating this term here, if you add 1 to the power, you get x to the minus 1, and dividing 32 by minus 1 is minus 32. Here, the x power is going to raise to x squared, so this then becomes 3 over 2. Here, you end up with minus 8x. Once again, we now know the bounds here, so we know it's between 4 and 2. So if we just set up our brackets for 2, once we'll do this with 4, so minus 32, and 4 to the power minus 1, plus 3 over 2 lots of 4 squared, minus 8 lots of 4, minus from this, doing it all again with 2, so minus 32, 2 to the power minus 1, plus 3 over 2, 2 squared, minus 8 lots of 2. You can, of course, plug this all into your calculator all at once, but if you wanted to just work it through, you end up in the first bracket with minus 8. This then comes to plus 24, and that is minus 32. Then over here, you end up with minus 16 plus 6 minus 16, which will be the same as this first bracket. So minus 8 minus 32 is minus 40. Then add 24 onto that. You just are left with minus 16 minus, and here, minus 16 minus another 16 is minus 32. Add 6 onto that, then just becomes minus 26. So minus 26. Minus of a minus is like a plus, so minus 16 plus 26 gives us an area for the integral underneath that bit of the curve of 10. Then just finally combining the two together, so 10 add the 36 gives us an area of R of 46, which was what we had to show.